Okay, so this is a continuation of the iterative techniques that I presented, the flexibility and the stiffness formulation. So for this third one, the Holzers method actually captures your intermediate modes. Actually, it can also capture your fundamental and your last mode for as long as your program is quite good in iterating the value of omega on the basis of a formulation of stiffness and uh, displacement theories. So if we consider the stiffness formula, force is equal to the stiffness times displacement, and assuming a trial displacement vector A, recalling that your K from your frequency equation, omega, is simply the square root of K over M. Okay, so we can actually use this to relate the mass and the stiffness. Hence, we get from the stiffness formula this equation here, which is very important in the Holzers approach to the determination of the natural frequency. And note that the above formula is applicable to each mass assuming relative coordinates 1, 2, and 3. Okay, so this can be very well understood by looking into the model as a shear building model. So if we have here a 3-story building, okay, your displacement considered here are both the absolute and the relative displacement. Normally you call this the drift. Okay, so if this is your first story drift, and this is your second story drift, this is your third story drift, okay, your amplitudes are actually measured in the absolute form. Okay, so these are now your A, it is your A3, your A2, and your A1. Okay, you start from the second floor. Okay, so this is your A0, 0, 1, 2, 3. While your relative magnitudes are actually delta 1, delta 2, and delta 3, such that delta 3, delta 2, and delta 1, such that your delta 3 is simply A3 minus A2. So A2 is equal to A3 minus delta 3. So that's now the formulation we're going to use in the Holzers method. But this is equivalent to the spring mass system that the problems actually presenting above, no? So this is actually the same as the previous problem. So taking note of the formulation, we can compute now for the forces in each story that will give you your amplitudes on the basis of the Ka. Okay, so force is equal to stiffness, which is omega squared m times the area. Okay, so this is simply F is equal to K times, not the area, the amplitude, I mean, or the displacement. Okay, so for F3, F2, and F1, there will only be changes with the subscript, and taking note of the shear forces now in each spring, which is computed on the basis of absolute displacement of each masses, we note that if you have an an F1, F2, F3 on the situated or applied on the shear building model. So this is the building. So this is F3, F2, and F1. So the total shear at each story now will simply be, okay, your Q3 equals F3. Your shear here will be equal to Q2. You have to add Q3 plus F2. And then your Q1 here is equivalent to Q2, and you have to add F1. Or in short, Q3 is simply F3, Q2 is F3 plus F2, and Q1 is simply F3 plus F2 plus F1. Okay, so you can also look on it that way. Okay, so these are now the formula for the shear. Now, in order to get the relative displacement delta, the shear will now be used to yield the displacement by simply dividing it with the corresponding uh, K values or the stiffness values in each story. Okay, so the story means the spring. So therefore your delta 3 now becomes delta Q or Q3 divided by K3 and so on. And your amplitudes, as I have shown on the shear building model, A2, A1, and AO can simply be computed by subtracting your amplitude above with that of the relative displacement above. And the stopping criterion is such that your amplitude at the base must always be equivalent to 0. So there's no motion in the base. So to apply this in the problem, the solution will start by noting that the given mass and K are available. So let me now use an assumption or a trial value of A3, because we need A3 no, to start solving for the rest of the parameters. And of course, we also need a trial value of omega in order to solve for the rest of the parameters. So on the third story, so you're starting upward. Your F3 now can simply be solved by, because there's an assumption of A and omega, the mass is given. So F3 now becomes simply omega squared M3A3, and then Q3 is simply equal to F3. So there's now a smooth transition of the formula from force to shear to displacement, then to amplitudes. Okay, so this is now F3, Q3, delta 3, A2. Okay, and then A2, the second story, will be used. F2, Q2, delta 2, A1, and then it will be used to solve for the first story, F1, Q1, delta 1, AO, and this AO now will give you a sign if you are going to stop the procedure. No? If not, you go back assuming another value of what? Another value of maybe A3 if you want to change it, but I only change this omega. It will suffice, no? In order to converge into a stopping criterion, converge into a solution that will set your stopping criterion to be satisfied, then you can change, just change your omega, and if you are now satisfied with the stopping criterion, then your omega is the real value, and normally, as I have told you, the Holzers method can capture the intermediate mode, including the first and the last mode. Okay, so this captures normally the intermediate modes, and the first and the last also, okay? The fundamental and the last. Okay, so I'll be showing you the program for you to be able to appreciate how MathCAD works uh, outside this video presentation. Thank you.